Okay, what we have here is my video reassessment for our most recent standard, the one-dimensional quantum mechanics standard. Um, Basically, I just felt like I should redo the standard question. It's a very in-depth question with many steps and just learn a lot from just going through the question. So that's why I decided to just do the question from the standard. And on top of that, I really didn't do well on the in-class standard at all. So I just thought it would be a good idea to redo the standard question. So just getting into it, it reads, show that for an infinite one-dimensional square wave of length L, you get the following quantized energies, which is here. Okay, and then also given in a problem is the Schrodinger equation, which of course you need with the quantum mechanics problem as such. So there's no way you could just bam, pop out, do some algebra, and just get the energies. You have to, the way I think about it is it's a process. You have to think about the problem in order to actually solve it. So in order to help my thought process, I had to draw the infinite square wave. I had to draw my infinite square wave. So basically what's going on here is inside the square wave, the potential energy is zero at the boundaries, which is x is equal to 0 and x is equal to L. You have infinite potential energy, which means that the particle cannot go there. There's no chance of finding a particle there, so therefore there and there the wave equation is 0. Okay, so just starting off with my Schrodinger's equation, I have to think about it. So I want to find the allowed energies for inside the square wave. So first of all, I have to think inside the square wave. I know my potential energy here is equal to 0. So therefore, the kinetic energy is just my only energy. So therefore, kinetic energy is equal to energy, as I got here. So therefore, that helps me change my Schrodinger's equation, which is just a second order differential equation. So now what I want to do is I want to basically solve the Schrodinger's equation. I want to solve the second order differential equation, and I do so by finding my wave equation, which is here, psi of x. So the first step that I need to take is in order to shorten my Schrodinger's equation, I could redefine this 2me over h bar squared as beta squared, making beta equal to the square root of 2me over h bar. Therefore, I once again rewrite my Schrodinger's equation with my new defined variable, and that's what I have here. So basically d phi squared with respect to x is equal to, well, the second derivative of phi with respect to x is equal to negative beta squared times, once again, my wave equation, which is what I'm trying to find. So, okay, getting into page 2. Basically, just right here, just starting off with what I left off with. So basically, what I need to do is I need to try to figure out. I need to try to solve for my wave equation. I need to try to figure out some solutions for phi of x that can solve this differential equation. So just from eyeballing it, you can see that, okay, the second derivative of phi of x has to be equal to phi of x times a constant squared, times a negative constant squared. So 2, we have to make an educated guess. We know that both the sine and cosine function gives you that. If you take the second derivative, you basically just get that times a constant squared. And that's what we have here. So therefore, I have phi1 of x. I go through the math. I see that it checks out. So that is definitely a solution. Phi2 of x is also definitely a solution. So they're okay. All right. Using superposition principle, which tells me if you have two solutions to a differential equation, then a general solution to that differential equation is the sum of those two solutions. So basically that's what I have here. We already said sine beta of x and cosine beta of x. We just proved that both of those were solution, and a and b are our constants. So therefore, now what we're trying to do is we're trying to figure out what is a and b. You know what I'm saying? What are these constants that I just added into my wave equation, my solution for the wave equation? So I use my boundary conditions to help eliminate one of these, because we know phi of x at 0 has to be equal to 0. We talked about earlier in our diagram. At that point in time, or at that point, the wave equation has to be equal to 0. That just comes with the understanding of the wave equation and what's going on at the boundaries. So therefore, I know cosine of 0 is equal to 1. So therefore, this can never be an actual solution or actually a helpful solution to our Schrodinger's equation. So this part, this cosine part, could be of no use to us. So therefore, we could eliminate that, and therefore we have our real. This is our actual helpful. Yeah, it's a solution mathematically, but it doesn't really help. It doesn't really fit into what we're looking for. So therefore, we have phi of x is equal to a sine beta of x, and this is our real. This is our real. Basically, this is our real wave equation. Okay. So therefore, oh yeah, using our boundary conditions again, we know phi of x when x is equal to 0 has to be equal to 0 because that's our other boundary. No, oh no, phi of x at x is equal to L is our other boundary, has to be equal to 0. So therefore, a sine beta times L has to be equal to 0. So therefore, we know just from trig, understanding of our trig functions, okay, sine of what gives you 0? Well, sine of any integer times pi gives you 0. So therefore, beta L must be equal to 0. We know beta has something to do with our energy. So therefore, that's why we're uh, dealing with beta L. So that's why we're because beta L has energy in it. So on to the next page. I'm over my time, but I'm trying to speed it up. This is it. Okay, just getting through it. So like we said, all right, started off right here. That is our solution to the wave equation. That's our wave equation. Okay, that's our solution. As I said, at L, x has to be equal to 0. Beta L is equal to n pi. So therefore, beta is equal to n pi over L. But we also already defined beta as the square root of 2me over h bar squared. Basically do some algebra, solve for E. And therefore, we just basically just doing algebra right here. But as we see that the allowed energy states for E is n squared over h squared 8ml squared. And that's it.